All right, for this series, we want to try to understand elements. Why do we care? Well, we care because chemistry is the foundation upon which we build biology. And so, while we don't want to delve too deep into chemistry, it is important to understand how things play together. This is going to be very important throughout all of the biology that we do this semester. And so, it's nice to start with a solid foundation. As we look here at the periodic table, there's a couple of things that we should be very familiar with. We can highlight those here. Certainly, how to read this box. That's an important thing that we have to be able to do. We have to understand what the atomic number is. We have to understand what the atomic weight is. Some of those other things useful, but maybe not so much. And like I alluded to just a minute ago, the whole purpose behind this is to understand how things play together. So with that in mind, let's come over here and let's discuss bonding. We can divide bonding into roughly two different types. Let's start with this. Let's start with intramolecular versus intermolecular. Of course, intermolecular, inter meaning between, so these are going to be between different molecules, holding one molecule to another. The intramolecular forces, or are the forces within the molecule itself holding the molecule together. And this is where we want to start today. And we can divide this up into ionic and covalent bond types. For intermolecular, and we'll talk more about this later, the only one that we're really interested is hydrogen bonding. Because this has to do with water, especially, and water is super important in biology. Biology happens in water, and so hydrogen bonding is critical to understand. There are certainly other types of intramolecular forces, and we're just not going to worry about it. The first thing I want to do is actually go, when we look at these intramolecular forces, ionic and covalent, I want to make sure we understand what they mean. So ionic, this is all about ionization, and then the principle of opposites attract. This is based on electrostatic attraction. Covalent bonding is more about sharing. And certainly as a caveat, there isn't any true ionic bond, there isn't any true covalent bond. All of the bonds we talk about are in actuality hybrids of these two, but that gets complicated and we're not going to go there. So we're just going to keep it clean and dry and discuss the differences between ionic versus covalent. Now, in order to do that, in order to understand that, we need to come back to our periodic table, and I want to highlight one key group, and that is this group here, the pink group. Pink, pretty, princess, whatever you want to call it. These guys think they're special, and as such, they actually get a cool title. These are what we call the noble gases. Why are they noble? Well, because they're kind of stuck up. They don't like playing with anybody. In fact, they don't need to play with anybody. They are non-reactive. Have you ever heard of helium dioxide? No, because it doesn't exist. What about sodium, neon? I can't throw those things together because neon is just neon. It doesn't exist or pair with anybody. These things are the epitome of stability. And in fact, as we look at the periodic table is all laid out to help us understand the stability of different elements. And if we understand their stability or their instability, we can begin to predict how they play together. That these guys, the noble gases, they don't play because they're stable. Now, to understand why, I want to highlight the numbers. So if we look at helium here, look at that number right there. It's 2. That number is 10. That number is 18. And remember, this is over here, this is the atomic number that we were looking at before. The atomic number, this represents the number of protons. But remember, protons are positively charged. And for every positive, at least in an unionized state, we have a negative. So this also represents the number of electrons because electrons are negatively charged. Okay, so helium has 2 protons and 2 electrons. Neon has 10 protons and 10 electrons. Argon has 18 protons and 18 electrons. This comprises what I like to call the octet rule, which simply put is the combination to my lunchbox 2, 8, 8. Now, take a second to appreciate that that's exactly how the periodic table is laid out. How many elements are in this first row? 2. How many elements are in the second row? 8. How many elements are in the third row? 8. That is actually important to understand because these values right here represent electron stability. All of the other elements want to be noble. They want to be like the noble gases. And what this means is that their valence shell is full. So we're going to say full valence shell. Now, the valence shell, don't get too freaked out over the term valence. The valence shell is just the outermost shell. And the periodic table of elements actually helps me understand how all of this stuff works. So let's take, for example, let's take chlorine. Okay, chlorine down here. Chlorine is number 17. Okay, if we think about what this means in terms of our octet rule, it means that for chlorine, there are, to get there, how many shells? Well, there's this first shell, there's this second shell, and there's this third shell. We'll come back in just a second to talk about what shells are. So in the first shell, we'll just draw that as a circle. How many electrons can this hold? This can hold 2 electrons. And we'll just draw them right there. There's the first shell. Second shell, here's the second shell right here. We'll draw another circle. How many electrons can the second shell hold? 8. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. Now remember, chlorine, because it's number 17 on the periodic table, has 17 electrons. So far, we've added 2 in the first shell, 8 in the second shell. That's a total of 10. We have 7 left. So let's go on to the third shell. The third shell represented by this third row. We'll draw another circle. How many electrons will the third shell hold? The third shell also holds 8. So we fill them. 1, 2, 3, 4, 5, 6, 7. Uh-oh, we only had 7 left. That's all of our 17 electrons. You can see if we were argon, we had 18, we would be able to fill that octet. But as it stands for chlorine, chlorine is missing 1 electron. Now that's a big deal. Chlorine really wants that 1 electron because all it needs is that 1 last electron in order to complete its valence shell. Let's contrast that with, say, sodium. Sodium on the periodic table. Sodium is right here, number 11. Because it's number 11, in an unionized state, it's going to have 11 electrons. 11, of course, tells me how many protons it has. So let's do the same thing. We've got sodium. First shell, how many? 2. We'll draw them here. Second shell in orange, how many? 8. That will bring us to 10. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2 is 10. Sodium has 11, so it's got 1 more electron. So we have to go to the third shell. So here's our third shell. It holds 8. It wants 8. But there's only 1 left. There's the electron configuration for sodium. You can see now that these two elements, sodium and chlorine, have very different problems. They have the same desire. The desire is to be like the noble gases. They want to fill their outer valence shell because that equals stability. And everything in nature is lazy. Everything wants to exist in the lowest energy state possible. And so as it seeks for that stability, it's going to try and find a way to satisfy this octet rule because this equals electron stability when there's a full valence shell. Now, what can chlorine do? Well, chlorine can steal. It doesn't matter where it gets it, right? At the end of the day, chlorine is going to steal an electron from somewhere to satisfy its valence shell. And as such, remember, there's only 17, there's plus 17 neutrons, but now there's negative 18 electrons. This is the process of ionization. Chlorine has just turned into chloride, negative 1 charge. Now again, it doesn't matter where it got its electron. The first opportunity that it has to steal an electron, it's going to take it. Now, consider sodium for a second. Sodium could try and steal how many electrons? 1, 2, 3, 4, 5, 6, 7. But if sodium stole 7 electrons, sodium would carry around a negative 7 charge. Nothing can carry around a negative 7 charge. Remember, we're trying to find the laziest state possible. And being negative 7 is not lazy. That's impossible. So that's not an option. However, what if walking down the street, it just decided to give away its electron? What if in the easiest reaction it could find, it just donated that electron to somebody? Now, this outer shell doesn't exist anymore, and this shell becomes its outer valence shell, and it's got all of the electrons in it. It satisfies the electron stability rule. The difference now is this. Sodium has plus 11, but it's only got for electrons -10, which means that sodium ionizes to become sodium ion, and it carries a +1 charge. Now let's contrast with one other. Let's look at, say, carbon. Carbon is right here, number 6 on the periodic table. We've got carbon. There's our first shell, 2 electrons. Here's our second shell. How many electrons does it hold? 8. But how many do I have left? Carbon only has 6 electrons to begin with. If 2 of them are in the first shell, how many are left? Just 4. So 1, 2, 3, 4. Carbon is really, really far away from the noble gases. It's as far away as you can get, right? Sodium was just away by 1, and it just got rid of 1. Chlorine was just away by 1, and it was able to steal 1. Carbon needs 4. Now, could it give away 4? That would require it carrying around a +4 charge. Could it steal 4? That would require it carrying around a -4 charge. Both of those charges are too high to be considered stable. So those aren't options. It can't steal, and it can't give away like the others. And now, with these 3 examples, we're able to understand the difference between ionic bonding versus covalent bonding. As a rule of thumb, it's not hard and fast, but for our purposes, it's going to work. As a rule of thumb, those elements that are close to the noble gases will ionize. That's going to include these rows here. Okay? The first column, the second column, these will ionize. These are going to become cations. And like we saw with sodium, this is going to be a monovalent cation because it's going to carry around a +1 charge. But if we look at its neighbor magnesium or calcium, these have 2 electrons in the outer shell that it's going to give away. So these are going to be divalent cations. This column will carry around a +2 charge. And that's about as high as we want to go as far as charge, considering stability. And then on the other end, we have the anions. And for our purposes, this last column right here, this is the only column that we're going to worry about for ionization. These are going to be the anions, and they will carry around a -1 charge. So column 1, column 1, column 2, and column 17, this is where we will find elements that will form ionic bonds. And why do they form ionic bonds? Because if we go back to our definition, ionic bonds means ionization, and we defined that as giving up or stealing electrons because they're so close, like chlorine would steal 1 or sodium would give 1 away. The ionic bond itself is an electrostatic attraction. In other words, just like magnets, opposites attract. So we go down here and we look at chloride ion, and it's a negative charge, and we look at sodium ion, and it's a positive charge. Positives and negatives attract each other. So those two things are going to come together simply because of charge, and we get sodium chloride, or common table salt. Now, just to drive the point home, what about something like magnesium chloride? How is that going to work? Well, remember, if we go back and we look at magnesium, magnesium is in this second column and is a divalent cation, right here, number 12, right? So magnesium carries around a 2+ charge. Chloride, as we know, carries around a -1 charge. So how many chlorides is it going to take to balance out the +2 charge of magnesium? It will take 2. So magnesium chloride will be 1 magnesium plus 2 chlorides, and that gives us MgCl2. And I know that these are held together by ionic bonds because chloride is here in column 17. It's an anion. Magnesium is over here in column 2. It's a divalent cation. All right. So there's the idea behind ionic bonding. Electrostatic interactions between full formal charges of ionized molecules. What about covalent bonding? Covalent bonding is all about sharing. And we come back to carbon as the perfect example of this. Carbon could not ionize. It would require giving away all of its electrons and having a +4, or stealing 4 electrons and having a -4. There is no partial ionization. It's all or nothing. And carbon just can't do it. So, what does it do? Well, it looks for other things that are willing to share electrons. Consider, for example, hydrogen. Hydrogen is number 1 on the periodic table, and as such has 1 electron in its outer valence shell. Hydrogen wants to. It wants to be like helium, to have that outer valence shell full. Well, what if these two shared? And then we have another hydrogen over here, and it shares. And another hydrogen over here, sharing. And another hydrogen over here, sharing. Now, what do we have? We have everybody's favorite gas, methane gas CH4. Hydrogen thinks it has 2, right? Here's hydrogen right here. And it's got this one, and it's got this one. We can see clearly what carbon thinks. Carbon thinks it's got all 8 in its outer shell, the 4 that it brought and the 4 that the 4 hydrogens brought. So in this way, everybody is satisfied because they think their valence shell is full. And this is how we can begin to understand bonding interactions. Okay, there's one last division that we have to cover. If we come back to covalent bond, we know this is all sharing, but sometimes sharing doesn't occur equally. So we can actually divide this up into 2 types of covalent bonds. We can call these polar covalent bonds and non-polar covalent bonds. Let's consider, again, just looking at these. I'm going to do that in a different color so that we don't confuse anything. Let's look at these elements right here. And we'll also throw hydrogen into the mix. Of course, hydrogen's way over on this end, but we'll come back to that in a minute. Of these 3 that we have down, which one wants electrons more? Oxygen, nitrogen, or carbon? Well, the closer they are to the noble gases, the stronger their desire for electrons. And we term that, we'll come down here. No, we'll stay up here. We term that concept electronegativity. Simply put, this can be defined as let's use a catchy word, lust for electrons. And again, the closer I am to the noble gases, the closer I am to having my valence shell full, the more electronegative I become. The more farther away, the more electropositive I become, the desire to give up electrons, like sodium. That's a very electropositive element. For us, this is going to be easy. We're gonna simplify this rule for the things that we care about in this class, and we're going to say oxygen is more electronegative than nitrogen, which is more electronegative than carbon, which is about the same as hydrogen. Now you think carbon and hydrogen, this is pretty easy to understand, because if we look, carbon, as we saw, well, let's come back down here. Carbon, as we saw, has 4 out of 8, right? In other words, its valence shell is 50%. Hydrogen, likewise, has 1 out of 2. This one's at 50%. Hydrogen is also at 50%. And so in percentage terms, they want electrons about the same. And therefore, our rule stands as it is. Oxygen wants electrons more than nitrogen, which wants them more than carbon, which wants electrons about the same as hydrogen. A polar covalent bond is simply a covalent bond in which there is a difference in electronegativity. Let's consider the perfect example of this, which is water. Okay? Now, to draw water, here's oxygen. Oxygen on the periodic table, if we come back here, is right here, number 8. So, if we play the same game that we did down here, we know that the first shell has 2 electrons in it, and then there are 6 in the second shell. We're just going to draw the second shell, and we're going to put those electrons down. We're going to put them right here. 1, 2, 3, 4. And then we backfill. We've got 2 left, so 5, 6. There's 6 electrons for oxygen. We can see that there are 2 vacancies, right? There's a vacancy there, and there's a vacancy there. Along comes hydrogen. And hydrogen, with its 1 electron, is able to come in and fill that vacancy. Now we have water, and we can draw this. It's very common to see water drawn like this. So we have our oxygen, and then we have these bonds, and on them we have the hydrogens. That bond right there represents these 2 electrons, right? The covalent bond represents 2 electrons being shared. It's a covalent sharing bond. Okay, now, when we think about it in those terms, let's apply this rule of electronegativity. These 2 electrons, they're kind of hanging out, right? They're hanging out around oxygen, but then they're also coming and they're hanging around hydrogen. I get that they're not orbiting like that, but in principle, that's what's going on. But who wants the electrons more? Oxygen is way more electronegative than hydrogen. Right? This is like the cool kid on the block that has the cool video games, and his mom's always making cookies and inviting all of his friends over for amazing dinners. Oxygen is way cooler to those electrons. And so those electrons hang out way more around here than they do around the hydrogen. And in reality, hydrogen gets very little of these electrons, right? We're just going to decrease some of this to show how pathetic hydrogen is. This creates a separation of charge. Remember, the electron is negatively charged. And if the negative is hanging out on the oxygen more, then we're going to have the opposite charge associated with the other end of the bond. So right across, right through the bond axis, right here, we develop partial charges. And the partial charge is shown by a lower Greek letter delta. And on this end, it's a partial negative charge. On the other end of the axis, we have a partial positive charge. Why do we call it a polar covalent bond? Because unequal sharing induces what we call a dipole. It leads to a dipole. And a dipole is defined simply by separation of charge. Okay, let's contrast that with methane that we have over here, right? Here we've got carbon, and it's bound to 4 hydrogens. Each one of these, again, 2 electrons per bond, making up a covalent bond. But based on our rule, carbon and hydrogen are about the same. In other words, these electrons are hanging out equally between carbon and hydrogen, and there is no dipole induced because neither one wants the electrons more than the other. And so in a nonpolar covalent bond, there is no separation of charge. Nonpolar equals no partial charges. And these are going to be very important in understanding intermolecular forces, specifically hydrogen bonding.